I would like to introduce the next speaker, Shang, who will talk about faster quantum sampling of Markov chains in non-regular graphs with fewer qubits. We look forward to your talk. Yun, please take it away.
Yeah, thank you. First, let me thank the organizers to give me this chance to give a talk here. My topic is about fast quantum sampling of Markov chains in non-regular graphs. I'm Yun Shang. I come from China. Sampling is one of fundamental problems in our daily life. But such as in network science, if we want to estimate the importance of internet reach, and sometimes we need to calculate the partition function in counting numbers, and all these problems can be reduced to sampling problems. We know quantum computing is one of the technology in the world, and it can speed up some more classical algorithms. Here, we want to use the quantum works based on Markov chains to speed up for sampling problems. First, let me give some basis about Markov chains and random walks. We know Markov chains can be regarded as a finite state, and it can be recognized as its transition matrix. And here we consider the special Markov chains, reversible Markov chains. It means that it satisfies the ergodic and detailed balance condition. The ergodic means there exists a unique stationary distribution. And random walks can be regarded as a special Markov chains. And there are two important properties we often considered. One is mixing time. It belongs to sampling problem. Mixing time means the time approximating stationary state. Another is heating time. It belongs to the search problem. Heating time means the expected time to hit the marked nodes. We know quantum walks is the quantization of random walks, and scheduled quantum walks can be regarded as a quantization of Markov chains, such as this is a Markov chains, and we select all the vertices for this Markov chains and copy it, and we can connect the left-right to the right points according to the original connection in the original Markov chains. Similarly, we can connect the right points to the left points according to the original connection. And then we can define the quantum walk operator W like this. And we can have the set quantum walks. By this, in this quantum walk operator, I stand for the reflection operator, V stand for the update operator, and S stand for the swap operator. And by this model, we can have the quadratic speed up for heating time when we detect the marked points. And use quantum walk algorithm, and we can speed up some sampling problems. Let's recall some more results. Some results use the simulated new algorithm. They need to construct a slowly evolving Markov chain sequence. And sometimes they use the idea to reverse the search problem, and such as continuous time quantum walk. And in this, we can use the same time complexity with heating time. And but this is only consider the page is known. And there are many problems unresolved for quantum sampling algorithm, such as this is the complexity for classical sampling. Although the quantum gap dependence reaches a quadratic speedup relativity to the classical case, the quantum time complexity X is extremely dependent on time mean. Second, quantum quadratic speedup of time complexity is only known for some special graphs or special stationary distributions. Third, no universal results are obtained for more general graphs corresponding to any reversible Markov-chain. In this work, we proposed a new quantum sampling algorithm, and we can use it to every reversible Markov-chain. Quantum sampling means preparing quantum states with amplitudes arbitrarily close to the square root of a stationary distribution. Our goal is we select a single vertex, and we want to evolve to the stationary distribution pair like this. And our results. We can accelerate nonregular graphs for both discrete and continuous cases, and keep the quantum speed up of existing quantum algorithm for regular graphs. At the same time, we can reduce the number of ancilla qubits compared with the existing quantum results. Now let's see the main algorithm scheme. This is our goal. And because in general, we didn't know, maybe we know the page. Page is the probability of the vertex G in the stationary distribution. Sometimes we know the page, sometimes we didn't know the page. In general, we didn't know the page. We divide the two cases to discuss. In case one, we use two techniques. One is quantum fast folding, another is interpolated quantum walks. And in this process, we get a byproduct. We construct a new reflection operator to do measurement. In case two, when page is unknown, we first need to estimate the value of page, and then we can reduce it to the case one to discuss. And in this case, we should use the noisy binary search algorithm. Then we can give the analysis of our results from the complexity and ancillary qubits. First, let's see the technique of quantum fast folding. Quantum fast folding means it can simulate the steps of a classical random walk action by square root of t steps of quantum walks. Like this, if we want to simulate this t steps of a classical quantum walks, if we use the quantum fast folding technique, we just use the square root of t, like this. And we construct the circuit for quantum fast folding, like this. And W stands for the walk operators. And we need the times to call the walk operators. This is similar to the phase estimation. And another technique we use is interpolated quantum walks. Quantum walks, now we can see how to construct the interpolated quantum walks. First, we have the regular walk P, like this. And we construct the absorbing walk P prime. P prime defined like this. That is, if we start from the marked points, it can only evolve into itself. Other is 0. Then we can construct the interpolated walks PS. It's a stationary distribution. How this we can construct the worker operator WS. Then, during the process, we need the discriminant matrix D. It defined like this, and similar for DS can be defined like this. Because DS has a close relation with the WS, that is, their spectrum have close relationship. This is the eigenvalues and eigenvectors for DS, defined like this. And this is the eigenvalues and eigenvectors of WS, it defined like this. From this, we can see they have the close relationship. And how this, we can give the approximate reflection construction. That is, if we do measurement, we want to estimate it is pi or not. We use this operator. And R pi changes the phase of pi and preserves the other phase roughly constant. And we give the circuit for the approximate reflection. This is the quantum fast forwarding process, and this is the inverse of quantum fast forwarding. And in general, if we construct a quantum walk algorithm, we often use phase estimation. Now we give the comparison between quantum fast forwarding and phase estimation. This is the number used in phase estimation. This is the number of ancilla qubits, is this. And this is the ancilla qubits used by quantum fast forwarding. From this, we found that we can reduce the ancilla numbers greatly. And now we consider our main results. Case 1, when page is known, we have this result. That is, for an quadratic reversible Markov-chain, we can get the state image close to pi with a constant success probability, and the corresponding complexity is this. Now let's see the process of proof. First, we select the randomly G and we input the quantum state G. Then we construct the interpolator work and we select the interpolator value S. And we construct the work operator WS. And this is the one eigenvector of WS. It has the overlap with the marked points and the unmarked points. Then we can construct the U-main operator by the quantum fast forwarding technique. This is the U-main operator, and we can use it on the initial state many times. Then we do measurement. And if we output pi, we stop the process. And for case 2, when page is unknown, this is our main result. That is, for any quadratic reversible Markov-chain, we can get a state close to the pi. And the complexity is this. Compared to the page is known case, we add this term. And let's see the proof of in order to estimate the pi g, we estimate pi g to be pi e. We need 3 steps. First, we give C copies of J as the input, and then use the U-main operator on the initial state. And if we do measurement, and if case 1, we can get the result. But if it is case 2, that is pi is not measured. And we go down the next step. That is, we will calculate the upper bound and low bound and medium, and then construct the U-main operator by the interpolator value SM. and then we can do measurement, and estimate pi is measured. If yes, we can stop, but if no, we go to this step. That is, we can use binary search to do the process iteratively, and then output the state pi. Now let's see the results comparison. We compared our results with the previous quantum results, and this is the classical complexity. This is our result. This is the best previous quantum results. We compare them from complexity ancilla qubit. For nonregular graph, our result is this, but for discrete time, its result. Obviously, this will reduce this term, and for this term we can reduce log. And for ancilla qubit, this is the existing results, but we can reduce the log from this, and this will over n. And for regular case, this is our result, and this is existing results. We reduce the log. And for ancilla qubit, this is our result, and this is existing result. And for regular results, people consider the continuous time quantum works, and this is the results. We have the same complexity, but when consider the ancilla qubit, we can get reduction using our results. And we give the application of our algorithm on some sparse graphs. We consider the 6 graphs, and this is a classical mixing time. This is our result. Compared to classical case, we found that we can get the quadratic speed up completely. And compared with the previous quantum results, in general, we can get the log reduction. Now let's see the summary. We propose a different quantum sampling algorithm by combining the quantum fast-forwarding algorithm with the interpolator work for all reversible Markov chains. Second, our quantum sampling algorithm displays a speed up compared with the existing quantum algorithm on non-regular graphs. And in some special graphs, especially sparse graphs, we achieve a completely quadratic speed up compared with the classical mixing time. And from this, we can see that our algorithm improves the sampling preparation in both the quantum case and the classical case. Now that's all. Thank you for your listening.
Wonderful. Thank you for this great talk, Shang. We welcome questions in the chat. David already shares good algorithm and detailed analysis. Thank you. Could you share more on achieving quadratic acceleration for any reversible Markov chain? How this will be in the future?
And we consider we just consider the for non-regular graph. We think we can't get the quadratic speed up. We just compared with the classical case existing quantum results, we can get the speed up like this. But on regular graphs, we can get the quadratic speed up like this by the heating time, and this for this epsilon we can get the log reduction compared with the quantum case.
Excellent. Shashi asks, can you describe the quantum walk operator? What gates does it use and how was it designed?
Oh, what's the quantum book operator?
Quantum walk operator. What gates does it use and how was it designed?
We use our main techniques is the quantum fast forwarding, and this is the quantum fast forwarding, and we use these techniques. That is for quantum fast forwarding. It can simulate classical random walks and use the quadratic speed up compared with the classical case. And in this T, we can, because it is for any T and T, we can design it. This is our technique.
Wonderful. Thank you so much for the great talk, Shang.